Hello everyone and welcome to the first 3D Buzz Math VTM. In these VTMs, we are going to introduce you to the ultra exciting world of mathematics.
Some would say exciting, others would say terrifying.
No, it's not that bad. It's all easy stuff, and we're going to prove it to you as we walk through this.
That's the plan.
My name is Zach Parrish. Many of you know me on 3dbuzz.com as Dark Viper 338, and joining me tonight is my very good friend, Mr.
Rob Rolnick, also known as Demondo on 3dbuzz.com.
Yeah, and I'm just going to call him Demondo as we progress through this. Demondo is going to be your guide as we go through this incredible journey of the world of math. I'm going to play the role of the lowly, know-nothing student. I'm going to bug Demondo with questions throughout the entire process. I'm going to make sure that he brings this down to everyone's level so that we all get to understand this.
Just no spitballs.
No spitballs, I promise. I'll try to keep them down to a minimum. Now, I should also tell you that this very first lesson is going to be a little bit on the basic side. We are going to reintroduce, you guys, kind of revisit the world of arithmetic. And we're going to be covering a lot of different topics. I'll let Demondo tell you exactly all the things we're going to be talking about here in just a second. But I just want to stress that if you have a bit of a mathematical background, you might find this first lesson to be a little bit slow. But this is where we lay the foundation. This is where we get you ready for some of the big topics we're going to be discussing later. Things like trigonometry, possibly some calculus as we move along.
Right.
So, Mr. Demondo, what are we going to be talking about tonight?
Well, tonight, this lesson covers the different types of numbers, the number line, rules to remember when multiplying or when saying two expressions are equal, etc., etc. In any case, I guess it's best now to jump in, get started.
Well, let's go. Come on.
So, I guess I should talk about the different types of numbers.
Okay.
But I'm sure everyone's thinking, why bother? Why have different types of numbers?
Well, I'm kind of wondering, because it's like, a number is a number, isn't it? We just use the numbers, and they all have their little things, so why do we have to dice them up into categories? It's just complicated.
Right. Well, not exactly right, I should
Okay.
say. Good try.
All right, well, I'm trying.
But the reason we divide numbers into categories is really for making rules work. Because you can say 2.5 is an even number. You could say it. It wouldn't make any sense.
Okay. Why is that?
Because even numbers, and odd numbers too, only apply to the integers.
Ah, there you go. So in order to make these rules apply, we have to divide the numbers up into specific categories.
Exactly. So when you say a proof or you use a theorem, you have to know if it can be used with the numbers you're working with.
You know which types of numbers are compatible with certain theorems.
Exactly.
Cool.
And these numbers aren't exactly self-exclusive. You'll notice that if you look at natural numbers, you'll see 1, 2, 3, and they're also under integers.
Ah, so some numbers belong in multiple categories.
Exactly.
That's very important to know.
Right. So,
also, I'd like to let everyone know that this list you see here that begins with integers and ends with whole numbers is listed in alphabetical order. There is no list of importance here. All categories are equal. Thank you.
Excellent. So, what are integers? Well, integers have any positive or negative number that don't have a decimal point.
Okay, so things like 1, 5, 57, negative 362.
Right.
Cool.
Meanwhile, irrational numbers are numbers that have decimal expansions that neither terminate or repeat.
Ooh, so like pi, for example.
Right, 3.1415, etc.
Yeah, it continues, but it never repeats, so that would be an irrational number.
Right, or you can make one up yourself. It doesn't have to be something everyone know, well, not everyone, but most people know of like pi. For instance, you can make one up, say, 0.1, 1, 2, 1, 2, 3.
1, 2, 3, 4, and just continue that until you die.
Yeah.
Rock on.
Except when you die, it terminates. So get someone else to continue.
Okay, there you go. It had to be a legacy, so yeah.
Natural, sometimes referred to as counting numbers, are the ones you learn when you're like 2, when you're counting on your fingers. 1, 2, 3, etc.
Is 0 included?
No. Well, kind of. There's a big debate among mathematicians whether 0 should be included in the natural numbers, or the whole numbers.
Okay,
but
so the jury's kind of still out, but for our purposes, what are we going to say?
We're going to say no.
Okay, there you go.
Rational numbers are kind of like the decimal numbers that do terminate, or do repeat. Essentially, they're the decimal expansions that are not irrational numbers.
So things like 0.5 or
0.6666,
0.333, 0.1222222.
Exactly. A good way to think of them is that they can be expressed as a fraction of two integers.
Ah. Okay, cool.
Real numbers is everything we talked about currently, most of what we're going to be talking about in the first few lessons, and unless stated otherwise, everything we talk about.
So we're not really going to be stretching away from real numbers very often throughout this series.
not just yet.
Okay.
So, unless I say something crazy like, I have an imaginary number, which isn't real.
Imaginary numbers. Cool.
Right. Don't worry about those just yet.
Okay.
But that would be an example of something that's not real.
Is 11T1 an imaginary number?
No, that's just something you made up.
Oh, okay. Fair enough.
And whole numbers are essentially the natural numbers including 0.
Okay, cool. I got it. Excellent work.
Excellent. So that's the different types of numbers that we'll be dealing with primarily.
Now, are there other types of numbers besides these?
Well, like I said, there's the imaginary numbers. Or imaginary number. There's actually only one of them. We'll get into that later.
Okay. Now, if we're talking about the different categories of numbers, do we always have to write out the word irrational number? Or do we have to write out integers? Yeah.
Well, it helps in math to have letters to represent these.
You know these mathematicians. They got to have symbols, man. Symbols for everything.
So, if I grab the ballpoint pen and I wanted to say integers, I just write a Z, but make it double struck. So it looks something like that.
So it's got like an extra line in it.
Essentially, yeah.
Cool.
Natural numbers are sometimes written as an N with an extra line. Double struck N. Rational numbers is a double struck Q. I draw them like that.
Letters with extra lines in them.
Exactly.
That's what this is all about.
That's essentially not to confuse them with if I use Q as a variable.
Right. So it's just kind of an example of some of the symbols here.
Right. And real numbers are a double struck R.
Gotcha. That's pretty good writing for using a mouse. I'm impressed.
Yeah, well, tablets always kind of gave me trouble, and I'm weird, so...
I'm with you.
Anyway, those are the letters that represent real numbers, rational numbers, natural numbers, and integers.
Excellent. You gotta get out of the ballpoint pen tool.
Next slide.
Yeah.
The different types of numbers, part 2. So these are just some basic terminology that you'll come across when talking about... mostly integers in these cases. Okay. So even numbers are any integer that divides by 2 to yield an integer.
Ooh. So things like 2, 4, 6, 8,
right.
122.
Right. So if you take any integer and multiply it by 2, you'll get an even number.
There you go.
So if you took another type of numbers, another integer, I should say, and divide it by 2, say 3, and you get 1.5 in that case. Right. That's an odd number. It doesn't divide cleanly by 2, and it's an integer.
Excellent. So that's where odd numbers come in, things that don't divide by 2 cleanly.
Right. So if you want to generate an odd number, you take any integer that you have, multiply it by 2, and then add or subtract 1.
There you go. Just step 1 away from it.
Exactly. Awesome. Because the number line, as I'll show in a second, goes even, odd, even, odd, even, odd, or odd, even, odd, even, odd, even, depending where you start from.
Okay.
Prime numbers are any positive integer that has exactly 2 factors.
So it's not at least 2 factors, it's just exactly 2 factors.
Right. So essentially it only divides cleanly by that number and 1.
So 1 and itself are its only factors. Like
right.
7.
7, 13, 29.
How many primes can you list off the top of your head?
Okay. 1 is not prime, I should say that. Okay. So I'll use the number...
Okay, we'll get to that. All right, I didn't mean to put you on the spot. Sorry.
I can do it, but okay, cool.
We'll get there.
Fine, cool. Composite numbers are any positive integer with more than 2 factors.
So can you say that if a number is not prime, it is a composite?
If you're talking about numbers greater than 1.
Okay. All right, cool. Awesome.
And they're integers, of course.
So it's got more than 2 factors, so it'd be like, I don't know, 22.
Yeah.
Yeah, I think so. Okay, awesome.
But of course, they have to be integers, so they can't just be more than 1.
Right, exactly. All right, very cool.
So, like I just said, there's 2 important things to remember. One is that one is neither prime or composite. I actually wrote that as number 2.
That's fine.
And the other important one is there are infinitely many prime numbers.
Ooh.
And this is one of those proofs that I find kind of interesting, so I'm going to jump into Photoshop for a second to actually illustrate it for you.
Oh, he's whipping out the Wacom tablet.
I know.
Everybody brace yourself.
Fear the bad handwriting.
Yeah, it's all good.
So anyway, say I had finitely many prime numbers. So I don't know how many I have. There could be 100, there could be 1,000,000, there could be 100 million.
All right.
So I'll just write them all out. So I've
You're going to write 100 million numbers?
P1, P2 for prime 1, prime 2,
yeah. ...
Pn, n being the final prime number.
All right. So this is assuming that there is a finite number of primes.
Right.
Okay.
And we just multiplied them all together. So 2 times 3 times whatever the last prime is, all the way up to that.
It'd be a big number.
It would be a big number. Now, that has to be a new number.
Sure.
Because we just multiplied a whole bunch.
Right.
But now let's say I went something crazy and I said, what happens if I add 1? Or subtracted 1 would work too.
So if you take all the prime numbers, let's say
if there were a finite
if there was
many.
a finite number, if you took all of them, multiplied them all together, and then added 1, you would have a new prime number.
Right, because think about it. You can't divide it by any of the primes.
Right.
Because we just included them all. And you'd have an extra part. And that means this new number would only divide by itself and 1.
I gotcha. So, in a way, we just proved that there are an infinite number of prime numbers, because you could just do that over and over and over for infinity and always get a new prime number.
Right.
Cool.
So, that's called a proof by contradiction, where you assume something is true and then prove that it can't be true.
There you go.
So now we'll jump back into our PowerPoint.
All right.
And we'll move on. If you wanted to find prime numbers, and I'll admit this isn't the most efficient way now that we have modern computer equipment.
Sure, just type Google all the prime numbers.
I doubt you get them all, but, you get a whole bunch of them.
Yeah.
But let's say you wanted to find them. Well, this famous mathematician, Zach can pronounce his name.
It looks like Eratosthenes.
Excellent. Devised a sieve to find these prime numbers. It basically works like this. You cross out 1 because that's not prime. Then you circle 2 because that is prime.
Okay.
And you start crossing off all the multiples of 2. I'm not going to do them all because...
Oh, go ahead. You've only got a few there.
Okay, so you cross out all the multiples of 2. And I don't know if I missed any, but it should be anything... It should be anything even greater than 2.
I think you did a good job.
Then you take 3, because that's now the next number in the line.
Right.
That's prime. And you cross out multiples of 3. So 9, 12, 15, 18, 21, 24, 27... And you keep doing this. So you do 5, and 10, 15, 20, 25. And you keep going.
Okay.
Every number that will end up circled is prime.
Oh, go ahead and finish it off. We're almost done.
Okay.
Come on. Circle 7.
7's prime.
Yeah.
11 is prime.
Yeah.
Well, 13 is prime. 19 and 17 are both prime.
Yeah.
23 is prime. And 29 is prime.
See, we were already done. We just had to finish circling.
Right.
Awesome.
Now, that's not to say these are all the primes, of course.
No, because you'd have to take every single number between 1 and, well, really, really high number. We won't even get into all that. And you'd have to do this to all those numbers.
And we just proved you can't, because there's infinitely many.
Exactly. So you'd spend a really long time
accomplishing nothing.
Yeah. Just pretty much proving that infinity will never happen in your lifetime. So here we go. From here we can get to the importance of prime numbers, because I'm sure what's the point is what a lot of people are thinking right now. Yeah, sure.
Well, the concept is that the fundamental theorem of arithmetic, also known as the unique factorization theorem, is a whole bunch of fancy words to say one simple thing.
What is that?
Any integer greater than 1 can be represented uniquely as a product of its primes.
So if you take its primes and multiply them together, you get that number.
And you can only do that in one way.
Oh, cool. Show it. I want to see.
Okay, so we'll jump back into Photoshop quickly.
I want proof.
Give me a number.
28.
28. So we'll use a handy tool known as a dichotomous key and break down 28. 28 is 2.
Man, you weren't kidding about the handwriting, were you?
No, I have a really bad handwriting. And
kidding.
14.
All right, so you have 2 times 14.
And then you have break 14 down into 2 and 7.
Okay.
And then you circle all the primes that you get at the end. That's 7. Kind of looks horrible. And those are the prime factorization of 28.
Right, and if you were to multiply all those together, you get 28 again.
Exactly.
Cool.
And now we'll jump back into the PowerPoint and move on to the next slide.
Excellent. Let's go.
Next slide.
Yeah.
The number line.
Ooh, I've seen this before.
Have you? Grade school?
Yeah, a long time ago.
Wow. In any case, the number line helps you visualize numbers. The reason a number line helps is because I could tell you have 3 apples and lay 3 apples on the table.
Sure.
And you'll see the apples. And you kind of maybe will get the idea of what 3 is.
Right, but 3 is still a concept.
Right, it's not something tangible.
Right, the apples are there. I mean, you can touch the apples. You could eat one. I'd like an apple right now, actually, if you had one lying around. But you can't actually see the 3 part. There is no real 3.
Right. So the number line kind of makes numbers more visual.
Right.
So
how does the number line work? I mean, when we stare at it, what are we actually seeing here?
Okay. Well, if you're looking at, I'll call it the center of the number line, you're looking at 0.
Okay.
And then you can go to either side of 0 and it's common to make the left negative and the right positive. That's not really required.
Right, but that's just it's kind of the standard.
Right, but, it doesn't really matter. One side is negative, the other is positive.
Mm-hmm. For our purposes, we'll use
the one shown.
Left being negative, right being positive.
Exactly. So in any case, you measure a certain length, and you call that the base length. So the length shown for between 0 and 1 is our base length.
Okay.
If you move that far from 0, you're 1 unit away.
All right.
If you move that far from 0 in the same direction again, you're now 2 units away.
Right, gotcha.
So basically, if you add, you're saying, okay, I want to move 2 units away, and then I want to move another 3 units away from my current position. And you say 2 plus 3.
Okay.
And you go, okay, so you start by moving 2 units, 1, 2. And if I want to move 3 units, you go 3, 4, 5. And now you have 5 units away from 0.
So if you say something like, I want to take 1 and add 3. Mm-hmm. So you start off 1 unit away, you add 3 more units, and you end up at 4.
Right.
Excellent.
And this concept of subtracting is the same thing as just adding a quote-unquote negative number.
Right. We're just moving in the opposite direction.
Right, it's basically stepping backwards.
Yes, exactly. Very cool. In this case, stepping to the left.
Right. So this should make it really easy to see those rational numbers that we were talking about, numbers that cleanly divide. Because if I say 2/3, then I take the amount of distance between 0 and 1, break it down into 3 equal amounts.
So let's see, I can find the pen tool. It's around here somewhere. There we go. I just made a little red mark to find out where it was. So if you said 2/3, we could take the space between 0 and 1, and we could divide it up into what I'm going to assume are 3 equal sections. And this would be 1/3, and this would be 2/3.
Exactly.
So we'd know we'd need to be right here at this spot.
Right. But then you get to a problem.
How's that?
What happens for those irrational, those crazy numbers that you kind of don't have an evenly divisible point to hit?
Right, because they don't repeat and they never terminate. So
right, so you can't really say, well, it's here, by just looking at the number line and breaking it down into pieces.
So what do you do?
Well, I'm going to give an example for a very specific irrational number.
Okay.
But you can come up with examples for other ones as well.
All right.
So again, I'm going to jump into Photoshop, and I'm going to... Excellent. I am going to draw a very shoddy number line.
All right.
Imagine that's straight, and that's 1 unit in length.
I'm trying.
I know it's hard. My artistic skills are...
That's okay. We forgive you.
Okay, so I'll actually change that a little. That's the 0 point on the number line.
Okay.
And that's 1 unit away.
Gotcha.
And this will be 2 units away. Imagine they're all evenly spaced.
I'm with you. That's excellent. In fact, that's probably a better number line than I could have drawn. Good work.
So now you go up 1 unit vertically.
Uh-huh.
So this is also 1 unit. And if you draw this diagonal line, by a theorem that we'll be talking about in a very quickly approaching lesson, not this one though, we're going to prove that this line right here is root 2.
The square root of 2.
Yes, 2. Look at that fancy 2.
That's a really scary 2. But
mutant 2.
While you're pretending that all of this is straight and evenly spaced, go ahead and pretend that that's a 2.
Exactly. So that length is 2. Now if we wanted...
That length
root
is
2.
The square root of
2. That's
exactly.
Right. So now if I measured this length and then arced it, so I kind of arced it and I brought it down, it would hit, let's say, here on the... it's a little far, but we'll imagine this is the root 2. It's actually a little before 1/2.
Right.
Or 1.5 actually, a little before that. But this a little far. But if we angled it and we dropped it and everything was measured to scale.
Basically, if you took this line and you rotated it downwards,
right,
and then measured out where its endpoint lied on the number line, you'd actually have the position on the number line for the square root of 2.
Right, which would be roughly 1.4142, etc.
Wow, you just pulled that right out of your head. That's not bad.
Like you said, I'm a math genius.
Yeah, that's just scary. All right, well, let's keep on jamming.
Right. So, jumping back into PowerPoint.
Back to PowerPoint.
You can also define regions in the number line. So, let's say I wanted every number greater than 2. I'd use the greater than symbol. Or less than 2, the less than symbol.
Okay, well, here, hang on. Let me come in here. I'm going to knock Demondo out of the way for just a second. Let's grab the good old...
Stop hitting me.
Yeah, I'm not trying to. Oh, look at this. The eraser tool is actually working like an eraser. So if we were to use something like the ballpoint pen tool and we said every number that is greater than 1. Now, again, I've lost my icon. There we go. So we say every number that is greater than 1. What we mean is everything that is, in this case, to the right of 1.
Exactly.
Keep right on going.
Now, what some people would do is if they want to say greater than 1 only, is they draw a non-darkened circle at 1 to say, hey, look, it's starting here, but that point is not included.
Ah, gotcha. So if it needed to be included, where you'd say something like greater than and equal, then what do you do?
Well, you can draw a double-struck bottom to it, like that, and then you just darken the dot. And usually the dot is really, really small, and it's solidly darkened, and everything's good.
So if you said, like, less than -1, hang on, I keep losing my icon, so...
It is kind of small.
If we say less than -1, it would just be a non-filled-in circle.
Right.
And then we would color all this in?
Right, exactly.
Gotcha. But if we said, here, let's go ahead and draw it. So that would be less than -1. If we said less than or equal to, we would double strike this and go ahead and fill in the circle.
Perfect.
Cool. I'm learning.
It's also important to realize that the number line is not stuck between -3 and 3.
No, clearly. We've already seen over here that it's already marked as going toward infinity in both directions.
Right.
So.
And without getting too fancy and trying to explain what infinity is, for our purposes right now, even though this is a pretty shoddy description if you're familiar with mathematics, think of it as the biggest number you can and bigger than that.
Okay. You got to realize that infinity is not really a number. It's just a concept, and for our purposes, you can just think of it as something too big to understand.
Right.
So where are we going from here? We just talked about less than and greater than symbols.
And we already mentioned how it makes it easy to understand addition and subtraction.
Gotcha.
Multiplication is basically addition several times. So 3 times 5 is adding 3 5 times.
Gotcha.
And division, we talked about breaking up an area.
Yeah, division, we actually already talked about a little bit when we said the 2/3 example. Where did my cursor go? There it is. When I took like 1 and I divided it into 3 segments, because that's exactly how division would be. If you said 1 divided by 3, well, you'd chop it up into 3 segments like so, and then here's your answer.
Right. So now we'll move on to the next slide, and we're going to be talking about basic properties of equations.
Ooh.
Now, some of these are going to be a little obvious, you might think.
Sure.
Like the reflexive property. If I say 5 is equal to 5...
Everybody kind of goes, duh.
Yeah, they're kind of like, what's the point?
Right.
But these are just very important fundamentals that you have to realize.
Okay, cool.
Before I continue, though, I'd like to point out that, yes, there's A's, B's, C's on this page. It's very scary. They're all in red.
Yeah, it's like, these aren't numbers. These are letters. Why are they here? I'm afraid.
But
Help me, Demondo.
I'm using these letters to represent any real number. So it doesn't matter what real number is on for A, but so long as you keep using the same one, it's fine.
Gotcha. They're called variables, and we'll discuss them in depth later on.
Probably in the next lesson.
There you go.
So substitution is basically saying, let's say I had a ridiculously long equation on the left side of my equal sign, and a ridiculously long equation on the right side of my equal sign.
Okay.
And you really are looking at that and you're going, ow, my head hurts, as frequently happens to anyone in mathematics.
Sure.
Well, let's say you look at a very small component of the left side, and you say, wait, I know that, for instance, 4 plus 1 is equal to 5. Then anywhere I saw 4 plus 1, I could replace that with 5.
And start simplifying things by substituting what you know.
Exactly.
I gotcha.
So that's the concept of substitution.
Cool. Can you give us an example? I mean, I hate to pest you, but could you maybe go into Photoshop and write something out?
I can try.
Come on, give it a shot. Live
on
adventurously.
the spot.
Yeah.
Something
in the hot seat. Just anything.
Okay.
Yeah.
Let's say I had something like sine. This is a function. Don't worry if you don't understand it just yet.
Okay.
Of 0 squared plus 3 all over 2.
Oh, man, I'm already confused.
Well, this would confuse many people when they first see it.
Sure.
Because sine of 0 is a function thrown in there, then it's plus 3 divided by 2, all of it divided by 2, actually.
We just scared off half our audience. How can we bring them back? Come on.
Well, you can realize maybe that sine of 0 is 0.
Ah.
So you make that substitution. Now you have 0 squared plus 3 divided by 2. And then you might say, hey, wait, 0 squared is 0. So cross that out.
Ah,
now you have 3 halves.
Okay, gotcha. Excellent. So what you've done is you've substituted what you know to simplify and make things easier to solve.
Right.
Excellent.
That's exactly what the substitution concept
Well, let's
says.
go then.
So jumping back into PowerPoint again.
Good work on the spot there.
Thanks.
I was impressed.
It's a talent and skill that you may never understand.
That's true. All right, keep rolling.
Symmetric basically says that it doesn't matter on what side of the equal sign you are. If you say something like 4 plus 1 equals 6 minus 1.
Okay.
Then it doesn't matter if you say that or you say 6 minus 1 equals 4 plus 1.
Right, because it's all going to be 5 however you dice it up.
Right.
Gotcha. Very cool.
And the transitive property basically says that if I say 4 minus 1 is equal to 5. No, 4 minus 1 is equal to 3.
Okay, I'm with you.
I can do math in my head, honest.
It's all good, no problem.
If I say 4 minus 1 is equal to 3, and I say 2 plus 1 is equal to 3, then I know that 4 minus 1 is equal to 2 plus 1.
Gotcha, excellent. So it's just kind of a way to progressively move along and realize that the first term and the third term are the same thing.
Exactly.
Gotcha.
So, jumping on to the next slide, we get into some very important properties of addition and multiplication.
Ooh, lots of letters and symbols and...
And, you know, that weird diagonal line there.
I'm scared.
Be scared. Be afraid.
No.
But not for long.
Yeah, okay.
Because I'm going to make this simple.
Good, here we go.
Okay, so, the associative property basically says that it doesn't matter if you add the first... Let's say you're going 1 plus 2 plus 3. It doesn't matter if you go 1 plus 2 is 3, and then add 3. So say that's 6. Or if you go 2 plus 3 is 5, and then add 1.
So the order in which you add is irrelevant.
Exactly.
Gotcha.
Same thing for multiplying.
All right.
Closure basically says that if you're adding two real numbers, you're going to get a real number.
Okay, so you're not going to break out of the real number world.
Right. You're not suddenly going to say, oh my god, I'm in this black, dark void of nothingness.
Okay, I gotcha.
Similarly for multiplication.
All right.
Commutative basically says that if I'm going to add two numbers, it doesn't matter if I go 3 plus 1 or 1 plus 3.
Okay.
Which kind of seems pretty much making sense immediately.
It seems really basic, yeah.
Same thing for multiplication. The distributive property is unique to multiplication.
Okay, so that's why you have that sliced line there, because it doesn't really apply to addition.
Right. It's basically saying if you want to multiply something, but first you want to add two terms, because of the parentheses there.
I gotcha.
You can instead do the multiplication and then the addition if you do it as follows. So let's say I had... I'll actually give an example in Photoshop, because it will be more clear.
Please.
Let's say I had, I don't know, 5... notice I'm not putting the multiplication sign. That's just how I learned to do it when I started using brackets.
That's fine.
You can keep it there if you'd like. 5 times 3 plus 1. Well, you can say that equals 5 times 4, which equals 20. Or you can say that 5 times 3 plus 5 times 1 equals 15 plus 5.
Which equals 20.
Which equals 20.
Gotcha.
So essentially it's telling you how you can distribute the 5 to both terms inside the brackets, or if there was 3 terms to all 3, etc., etc.,
Okay.
and not change what you're saying. It still gets the same result.
That makes sense.
The identity basically says that there exists a number that when you add by it, you're not changing your expression. So, say I say 5 plus 0 is 5.
Okay.
0 is the identity in addition.
Ah, I see.
Similarly, in multiplication, there is an identity. It's not 0 this time, it's 1.
It's 1. Because every time you multiply a number by 1, you get the same number.
Exactly.
Gotcha.
And inversion basically says that there exists a number that you can add by that will bring... that if you add it to your current number, you'll get the identity.
All right.
And same thing for multiplication. There exists a number that if you multiply by it, you'll get the identity.
I gotcha. So if you add any number, like let's say if we have 5, if you were to add negative 5, you get 0.
Which is the identity.
I gotcha.
If you had negative 5, you'd add 5.
Excellent. And with multiplication, it's kind of like adding a fraction of the number. How would that work?
Well, when you multiply, as we're going to show later, you multiply the numerator against the numerator and the denominator against the denominator.
Okay.
So, if you had a number, say 5, like we were using before, that's the same thing as saying I have 5 over 1.
All right, that makes sense.
And then if you do the reciprocal, which basically means the numerator becomes the denominator, numerator being what's on top,
Ooh, reciprocal,
and denominator
that's a big word.
becoming what's on the bottom.
Yeah.
If you reverse the top and bottom, so instead of having 5 over 1, you have 1 over 5, and you multiply, you get 1.
So it's kind of a long way of saying 5 times 1/5 equals 1.
Exactly.
Gotcha.
The important thing to remember, of course, is that you can't divide by 0.
Okay.
And I guess I'll tell you the reason for that right now.
Let's go ahead and move into that when we get into fractions. It'll be a lot easier then.
Fair enough. Don't worry, fractions are in this lesson, so it's not like 7 lessons from now.
What's on the next slide?
Well, these are just some other properties of expressions for addition and multiplication.
Okay.
If you're adding two numbers that are on the same side of the number line, so if they're both positive or they're both negative, then you get a number that's on the same side as the two numbers you add.
So two positive numbers added together will always yield a positive number.
Exactly.
Two negative numbers added together will always yield a negative number.
Exactly.
Gotcha. Cool.
Multiplication doesn't quite work like that. If you're multiplying two positive numbers, you'll still get a positive number. That's great.
That's easy to, yeah, I'm with that.
But if you're multiplying two negative numbers, you get a positive number.
Ooh, how does that work?
Well, here's the way that kind of makes it easy to understand.
Okay.
Think of two positive numbers as friends, because they're both positive.
Sure.
So they get along great. They have a positive relationship.
Okay.
Two negative numbers are also friends, because they're both negative.
Okay.
So they get along.
All right.
And therefore, they have a positive relationship.
So when you multiply two negative numbers together, you end up with a positive result.
Right.
Okay.
Another way you can look at this, if you want to know a bit more of the math of why it works, is to use the unique factorization theorem.
Ooh.
Which we talked about just before.
Yeah. How are you going to work this in?
Basically, you say something like this. If I have -5 and -3...
Okay, draw it out. Take us to Photoshop.
Okay, I'm actually going to change those numbers in if I'm taking it to Photoshop.
All right, let's do it.
Let's say I've got -21. That's a 2. That's a 1. They're both scary. That's the same as -1. And then times, because don't forget the fundamental theorem of arithmetic.
Right.
I can speak.
Every number is the product of its primes.
Right, uniquely.
Yes.
Only works for prime numbers, which are integers greater than 1.
Okay.
So you start by breaking out the -1.
Ah, okay.
And then you apply the prime factorization theorem. And you say that's 3 times 7. So 3 times 7. Then you have another number. We'll say we have -9. This is equal to -1 times 3 times 3. And we want to, that's a messed up 3. We want to multiply these two numbers.
Okay. So we're going to multiply -21 times -9. All right.
-21 times -9 equals 3 times 7 times 3 times 3 because of the
I gotcha.
properties we talked about before, meaning the order you multiply in doesn't matter.
That's right. We're using all of these primes together, and it doesn't matter the order that we put them in.
Times -1 times -1. But -1 times -1 is -1 squared.
Right. Okay.
And squares always give the positive value.
Wow. Okay.
It seems a little complicated, but it kind of makes sense when you use it, and it becomes second nature.
All right. Okay.
In any case, if two numbers on the same side of the number line get along great when you multiply.
Okay. So they always end up with a positive result.
Then two numbers on opposite sides fight. They don't see eye to eye. So you get a negative result.
Okay.
And that's all there is to know.
I gotcha. Very cool.
Okay, so I guess now the only thing to do is to jump to the next slide.
Let's do it.
So, as you can see by the title, this slide is going to be a fraction review.
Ooh, fractions. Gotta love fractions.
So, before we start talking about the addition, subtraction, etc., that you can do with fractions, let's get some terminology out of the way.
All right.
A fraction is composed of two parts, the numerator and the denominator.
Now, which one is which?
Well, in this horizontal method that you see due to typing,
right,
the numerator is on the left and the denominator is on the right.
So if we were to come down here and make sure we had the ballpoint pen tool, let's see, this would be the numerator, like so, and this would be the denominator, like so. Now when you're writing these out on a chalkboard, you'll often see these written out kind of like in this format. It'd be like A, which again is our numerator. I'm just going to kind of abbreviate. So that's numerator over, and this, well, you see again, and this guy here on the bottom is going to be your denominator.
Right.
So there you go.
And when you say over, you're talking about that line that divides the two.
Exactly.
Also, there's I'll call it a technique called reciprocation, which basically means you flip the fraction, and the denominator suddenly is the numerator, and the numerator is suddenly the denominator.
Right, so in this case, A and C would swap their places, but we'll talk about reciprocation here in just a moment.
Exactly. So, a fraction is just, as you can read, an elegant way of writing terminating or repeating decimals, or numbers with decimals.
Right, like 0.666 would actually be 2/3.
Exactly.
Gotcha.
So, addition. When you have two fractions, and they have the same denominator.
Okay, same number on the bottom.
Right. You add the numerators, and it's the denominator sticks.
All right.
So, as you can see, A over C plus B over C becomes A plus B all over C.
I gotcha. Excellent.
And subtraction, very similar.
Except you're using subtraction instead of addition.
Right, and you can even say, well, imagine B was negative. If B was negative 5, then, and A was 1 and C was 2.
I gotcha.
So you have 1 plus negative 5 all over 2.
I gotcha.
Which would be the same as 1 minus 5 over 2. In any case, moving on to multiplication. Multiplication is very simple. You multiply the numerators, and then you multiply the denominators.
Okay.
Very simple.
So you just kind of go straight across, and then you end up with new numbers on the other side.
Right.
All right. So how is that different from division?
Well, division is actually really simple once you understand multiplication. In essence, you take the reciprocal of the second term, so in this case, the B over D.
You flip it.
And then you multiply.
Okay. So here's what I want you to do. Let's challenge Demondo. Let's put Demondo on the spot. We have addition, subtraction, multiplication, and division. And what you're going to do now is go over to Photoshop, and you're going to demonstrate each and every one of these.
Each and every one.
Yeah.
Live.
That's right. So let's start off with addition of two fractions.
Give me two fractions.
1/7 and 5/8.
1/7 plus 5/8. Trying to make it all challenging by having them different.
All right.
No, I don't mind.
No, we'll keep things simple for the audience. We'll start 1/7 plus 3/7.
Okay.
We'll make it complex maybe at the end of this as a bonus.
Excellent. 1/7 plus, 3/7? Well, like I said, the denominator stays.
So if the denominator is the same, you just add the numerators.
Right. So 3 plus 1 gives 4.
Right.
And denominator stays the same. 7.
So there you go. So how does subtraction work? Well, let's say we have 5/7. Oh, let's change up the denominator.
Just change the order and switch it to subtraction. So now it's 3/7 minus 1/7.
Well, no, let's get something more. Let's say 5/8.
5/8
minus 3/8.
5/8. Fear my lopsided 8.
Yeah, I do.
Be afraid. Equals. Well, 5 minus 3.
You could say it's deflated. Anyway,
yes,
sorry.
You could. 5 minus 3 is 2.
That was bad.
Over 8.
2/8. So that denominator is not changing.
And I'm going to do something really quick, and I'm going to explain it as soon as we finish giving these 4 examples.
Okay.
I'm going to say that this is equal to 1/4.
Woohoo.
And I'll explain why this works after 2 more examples.
Coming up.
Okay.
So go ahead and clear that out, and let's talk about multiply. Well, I don't know, if you want to leave it up, that's fine.
I was going to leave it so we can...
Okay, go ahead and leave it up, and let's talk about multiplying two fractions.
Okay.
And this time we'll make things a little bit dicey. We'll say 1/7 and 5/16. No, you should have seen Demondo's eyes cut around when I gave him a huge number. All right, so
not a problem.
1/3. Just gonna change it. Get rid of the 5. Come on.
I'll keep it. No, I want it.
All right, fine.
5/16.
5/16. He wants big numbers.
Equals. So this will be a 5 on top. And then you have over 7 times 16, which is, just give me a sec to compute in my head. 5 divided by 112. That is
112.
I think.
That's right.
Rock on.
Yeah.
Now, thankfully, we're going to be doing
that was done in Demondo's head, courtesy of Texas Instruments, but we won't get into all that.
No, we won't.
All right. So how do we divide two fractions? Because we've seen how to multiply it. You just take the numbers straight across, and you end up with a new denominator and a new numerator. So how do we divide? And you can use any fractions you like. You can make them up this time if you want to.
Nope, using the same one as above.
All right.
I am very creative.
Yes, you are.
So, we're doing this division now. Instead of multiplication, as we had up here, it's now division. What you do is you say that you take the reciprocal of the second term. I'm putting a dot here to represent multiplication.
Okay.
You can do that instead of a cross.
Sure.
16 over 5.
So that's the reciprocal. You've taken the numerator and the denominator and you've swapped them.
This goes up here, and this goes down here.
Gotcha.
And now, without the help of Texas Instruments brain implant, I happen to know that 1 times 16 is 16.
And 7
times 5 is 35.
Nice. Excellent
So
work.
there we go. And that's those 4 basic operations.
Right. Now, as an added bonus, just because we like everybody here and everybody's awesome, I'm going to go ahead and hit backspace and clear this out. What would happen if we're going to add a couple of fractions together and it was something like 3/7? I'm actually writing with a mouse now, which I never do, so forgive me. So if 3/7,
almost looks like a question mark over 7.
It kind of is. Plus, and let's just make this like 1/5. What if the denominators don't match? What do you do?
What do you do?
Show us.
Must I?
Yes, you must. I'm putting the teacher on the spot.
Wow, I love it when students do this. Well, I'll do something clever. In math, there's actually 2 clever things you can do.
Okay.
You can add by 0, which doesn't change anything because we talked about it earlier, the identity. And you can multiply by 1.
Go ahead, keep going. I'm with you.
So, what I plan on doing is multiplying by 1 twice.
Ooh.
But if I multiplied by 1, you might be thinking, why? That's going to change nothing.
Everyone pause your brain for a minute. Before you go any further into what Demondo's saying, here's what we're going to do. We're going to jump over to PowerPoint. Now look at this. We have some consequences to these above fraction rules, if you will.
And other notes.
And other notes, yeah. So here's our first little consequence. If you multiply the numerator and denominator of a fraction by the same real number, you don't change the fraction's value. Why is this so important? Because in a second we're going to need it. That's why it's so important.
Right.
But what do we mean when we say this? Why don't we go over to Photoshop and show everybody real quick?
Okay, well, before I actually show you in Photoshop, I'm going to give you an oral words example.
All right, give it to me.
Let's say I had a birthday cake.
Okay.
And it was my birthday.
Happy birthday.
Thank you. I now take my cake and I divide it into 100 pieces, because I happen to like really small pieces.
I was going to say, it's not because you have 100 friends.
No, I certainly do not. So now I have 100 pieces. Even though I've got 100 pieces of cake, if I put them all together, I still have the full cake.
Right.
I still have one cake, the full thing I started with. So 100 100ths is 1. So what I'm going to do here is something kind of clever. Or I thought it was clever.
I think it's clever. I agree with you.
I'm going to multiply this one by 5 over 5. And it doesn't have to be 5 over 5. You can multiply it by any number of things. I can multiply it by 15 over 15.
Sure, it's still 1, however you dice it up. But the point here is that you're multiplying the numerator and the denominator by the exact same number, which is not going to change the overall fraction.
Right. So I happen to know that this will, I'm just going to write down here, that's 15 over 35.
Okay.
And this is also, I did this backwards just before when I said, what was it, 2/8 equals 1.
Right, but don't worry about that. Don't worry
or something like that.
So right now we've just multiplied the first term, the 3/7, by 5 over 5, and we now have 15 over 35.
Right, and I'm going to multiply it by 1/5 by 7 over 7.
Okay.
Which, I'll go right there, 7 over 7
all right.
equals. So then I go plus 7 over 35.
Ooh, look at this. Now the denominators match, so now you can add straight across.
Right. So you get 22 over 35. Now, this might be a little complicated because I'm going to say some fancy vocabulary right now, but don't worry. It's really simple. What you have to do, the trick to doing this, is you have to find the lowest common multiple between the two denominators.
Okay.
And what the lowest common multiple is, as you might imagine, it's the smallest number that can be evenly divided or cleanly divided by each of the denominators.
Right. Basically a number that both of these numbers will go into.
Right. And if you don't feel like calculating that, you can always just say, let's say I had 1/5, and you know what? I'll do it. I'll do it so you don't have to imagine it, because I can't even imagine it.
Go ahead.
So I had 1/5, and I don't know, plus 1/10.
All right.
I could say, you might realize that 1/5 is the same as 2/10.
Right.
By multiplying this side, the left side, by 2/2.
Sure.
So this is 2/10. But let's say I didn't know that 5 goes into 10. Or something.
Then you just temporarily forgot, because that could happen.
Yeah, it can happen to anyone. I can say, I can multiply the left side by the denominator from the right side over, it's like, let's say the denominator of the right side is 10, so 10 over 10. Times 1/5. And then plus multiply the right side by the denominator of the left side over itself.
Right, so 1/10 times 5/5.
I should probably put a time symbol there or something. Dot.
There you go.
5/5. And then you can solve.
So it's just a way to kind of convert your fractions to the same denominator so that you can add them together, because it's really tricky, kind of not possible, to add two fractions together don't have the same denominator.
Right. And if you do the second method where you don't find the lowest common multiple, then all you have to do afterwards is apply the prime factorization theorem that we talked about earlier.
Sure.
Break the numerator and the denominator into all of their prime components. And anytime you see the same number on the top and the bottom, you just cross each of them off.
Ooh. We won't worry about all that, though.
No, we won't.
Yeah, we'll keep things simple. We're just showing you a way that you can convert two fractions into numbers that can be added together.
Right.
In case the denominators don't match. So...
didn't mean to hit S.
Don't hit that. Let's go ahead and just clear that out. Let's jump back over to PowerPoint. And so that takes care of the if you multiply the numerator and denominator of a fraction by the same real number, you don't change the value. It's just like saying that 1/5 is the same as 2/10, is the same as 3/15, and so on, and so on, and so on.
And so on.
Yeah. So the next consequence that we run into, and this one is a little bit interesting, I can't find my cursor again, there it is the dividing by 0 results in an undefined result. So what on earth does that mean?
Well, that means something very specific. That means that, let's say I had a number, let's say 10.
Okay, we have 10.
And I divided 10 by 2.
All right, we end up with 5.
Right, now I divide 10 by 1.
Okay, we have 10.
Right.
I'm with you.
Now I divide 10 by a half.
Ooh, now this is where things get interesting. I know, just because I've done this a few times, that the answer is 20.
Right.
But how does the rest of the world know that? Let's show them that. If you take a number such as 10, and you were to divide it...
Actually, don't do it just like that. I'll fine, do it like that. That's cool. I'll show another way after.
Yeah. Divided by 1/2. Remember, 10 is the same...
It's 10 over 1.
It's 10 over 1. So, to divide, remember our rules. All we got to do is take our first term, it stays the same. Our second term gets flipped. We take the reciprocal, 2 over 1 now, and now we multiply. Let's put the dot. So this is going to actually equal 20 over 1, which, as we all know, is the same as 20. So 10 divided by 1/2 is now 20.
Right. And all I was going to say is that let's say you had 10 over 1/2, like that.
Ooh, now you're fancy.
Yeah, very fancy. A fraction under as the denominator. What you say, the memory aid is, much to my embarrassment. When dividing, don't be shy. Flip the denominator and multiply.
Oh, that's so cute. So we know that 10 divided by 1/2 is going to be 20. Right. 10 divided by 1/4, what's that going to be?
40.
10 divided by 1/8.
80.
80. Okay, there's a pattern going on here.
Right. As the denominator gets smaller,
closer to 0,
the result gets bigger.
That's right.
So herein lies the problem. If the denominator was 0, then you don't have a number to represent that.
Well, think of it this way. As we get closer and closer to 0, our result gets closer and closer to infinity.
Right.
Now, infinity is not a number.
Infinity's not a number. It's a concept.
Yeah, it's just a concept, which means there is no number for it. So if we make it all the way down to 0, there are no numbers left.
Right. It's undefined.
That's right. That's how we end up with undefined, which is also, for anybody out there who's coming to us with any sort of interest in computers, computer background, programming background, that's why sometimes a computer will spout off divide by 0. Some of the older computers were really bad about that.
I think Calculator even does that still in Windows.
Yep. It will. So, very cool. Awesome. That's why you cannot ever divide by 0.
Exactly. So we'll nuke that and jump back into PowerPoint very quickly. Now, with all this covered, we're going to jump to the next slide, which is almost the final slide. Exponent review.
Ooh, exponents.
When I get to exponents, I think of the relationship between addition and multiplication.
Okay.
Let's say I said 5 times 3. What I'm really doing is adding 5 3 times. So 5 plus 5 plus 5.
Right, would be 15.
Right, which is 5 times 3.
Exactly.
I think of that relationship, and I apply it between multiplication and exponents.
Ooh, I see. I gotcha. But
so
keep going.
5 to the power of 3
is the same as 5 times 5 times 5.
Right,
Yeah.
which is 125.
Yeah. I wasn't going to try to go that high. My brain would explode.
So, when you are multiplying exponents, if they have the same base, meaning, let's say in our example, 5 to the power of 3, the base would be 5, and the little small number in the upper right would be 3.
Okay, so what we're talking now are some rules with working with exponents.
Right.
Okay.
I lost the pen myself.
Yeah, it's real easy to do because it's just a single little red dot.
Exactly. So 5 being the base, and 3 being the exponent, 5 to the power of 3, which equals 125.
Gotcha.
If I had that, and I wanted to, I don't know, say I wanted...
Multiply it by maybe like 5 to the 6th power.
Okay, well I'm not going to compute that in my head.
You don't have to give us a final result, that's fine.
5 to the 6th, and I'll just, scratch that out because then it's not right.
We're not using that right now.
5 to the 6th times 5 to the 3 equals 5 to the 9.
So we've just taken the exponents and we've added them together.
Right.
And if you want to know what 5 to the 9th is, whip out your mighty Texas Instruments.
Yes, your mighty Texas Instruments.
Which Demanda would be doing if he wasn't talking. So what happens when you divide two numbers with exponents?
Well, if you're dividing two numbers with exponents, you end up subtracting.
Okay, as long as they have the same base.
Right. So that kind of might make you, well, exactly, as long as they have the same base. But if you realize that that's subtracting, then you kind of might catch on to the inversion property right now. But we'll get to that in a second.
Okay, keep going.
The identity basically says there is a value that you can use as an exponent that you're not changing the base.
All right.
It happens to be 1, because 5 to the power of 1 is 5 one time.
So any number to the power of 1 is going to be that same number over again.
Right. So inversion, if you think about division, it makes sense, because you say a to the minus b, or 5 to the minus 3.
So, okay, a negative exponent in this case.
Right.
Right.
Is the same as 1 over 5 third, or 5 to the 3.
Oh, okay, I'm with you,
Which would be 1 over 125.
Okay, cool.
And if you think about it, that makes sense, because you could say, well, if I have 1, and you look at the bottom, and you cheat, and you say, well, 5 to the 0 is 1, because of the unity property, which you see down at the bottom. And then you say, okay, and then I divide that by 5 to the 3. And I subtract, I'll have 0 minus 3, which is 5 to the minus 3. Do you want me to show that in Photoshop?
I think that'd be cool, because I kind of lost you there.
Okay, so what we're going to do is I'm going to just illustrate the unity property down here. We'll assume that you already know that. And we'll say...
any number to the power of 0 is always going to be 1.
Almost. There's the one exception that we'll get to when we get to the unity.
That's fine.
So let's say we have 5 to the 0
All right.
equals 1. We know this.
All right.
And we want to show how 5 to the minus 3 is the same as 1 over 5 thirds. Or 5 cubed, I should say.
Right.
Okay. So here's what we do. We say, we use our properties of when you have equality, and we say, instead of 1 over 5 third, we'll say equals 5 to the 0 over 5 thirds.
Okay.
I keep saying 5 thirds. I mean 5 cubed.
5 to the third is kind of what you're trying to say.
Or 5 cubed.
Right, I'm with you.
Anytime I said that, just erase that from your memory.
Okay, so using substitution, we've just taken that 1 and we're going to pop in 5 to the 0.
Right. And now using the property for division with exponents, we have this equals 5 to the 0 minus 3,
which is the same as negative 3.
Which is all the way over there.
Yeah.
And there you go.
Excellent.
So jumping back to PowerPoint, the power rule basically says if you calculate the exponent value first, and then take a new power of that.
Right. So if you have an exponent of everything that is inside 2 parentheses or brackets.
Right, and we'll give you an example in a second. Then you just multiply the exponents.
Right, you're kind of distributing that exterior exponent into the parentheses.
Exactly.
So go ahead and show us how that works.
Okay. So, nuke this, and we'll say something like 3 squared.
All right.
All squared. So, by our theory, that should be the same as 3 squared times 2. So, 3 to the 4th.
3 to the 4th power.
Equals 3 to the 4th. But how can we be sure? Well, you can say 3 squared is 9. 3 times 3. And 9 squared is 81. And then you just say, well, 3 times 3 is 9, times 3 is 27, times 3 is 81.
Awesome.
And granted, I'll say something up front.
Okay.
You can't give proofs by saying, hey, it works in this one case.
That's true.
Hey, in this one example, sine of 0 is 0.
Right.
Therefore, sine is always 0. You can't say that.
Okay.
But this has already been proven, and I'm not going to go into a whole bunch of complicated.
Absolutely.
I'm just showing that it does work.
Okay, cool.
So that's one way of showing it.
So there's all of our properties for working with exponents. Where do we go to next?
Well, now we talk about that one exception that I mentioned when working with the unity.
What's the exception?
0 to the 0. That's not 1.
I gotcha. What is that going to be?
It's going to be undefined, I believe.
Oh.
And the reason for that
all right.
is because of this. Let's say I had 0 cubed. That's 0 times 0 times 0, which is 0. But let's say I want 0 to the 0. So take 0 cubed divided by 0 cubed. Right?
Right, I'm with you.
So that's like 0 to cubed.
Yeah.
And then I have another cubed on the bottom, so it'd be 3 minus 3 when you work it out. And you'd have 0 to the 0. You'd say, hey, that should be 1.
Yeah.
But not quite. Because if you worked it out, you'd have 0 on the numerator of your fraction.
Right.
0 on your denominator of your fraction. And what just happened?
That. Yeah, you just have divide by 0.
Yeah.
So it's undivided.
Undivide.
Undefined is what I'm trying to say. It just didn't come out right.
Okay.
It happens. All right, cool.
So, with that done, we talk about the final thing in this lesson.
Ooh.
Order of operations. Now, order of operations has gone by numerous acronyms. If you say parentheses or you say brackets, the first letter changes.
Yeah.
Depending on how you find it easier to remember, you can say BEMDAS or BEDMAS or many others.
Right, but that's just because certain elements can be swapped back.
Right, and we'll explain that.
Right.
The other important thing to understand about order of operations is that nothing, not one thing that I've said currently, makes this a given. There's no reason that order of operations should exist. Maybe you'll say, maybe. Someone might say, well, the parentheses part makes sense. Do parentheses first.
Sure.
I can see that. But why would I do addition before multiplication? Because essentially you do operations in the order of operations.
Right.
So why would I do addition after multiplication? Why? Why can't I do it first?
Well, this is basically because a big group of mathematicians got together a really long time ago, and they're like, okay, this is too confusing, because if 2 separate people do the exact same math problem in 2 different ways, we get 2 different answers. We need a standard.
Right.
So they came together and came up with this order of operations that everybody has officially agreed upon.
Yes, it was this giant hand-to-hand, singing Kumbaya moment.
Exactly. It was all very sweet. But now we have this rule, this guideline that everybody follows to solve math equations with an order of operations. So we start with the numbers that are in parentheses and we go on.
Right. I'm going to put little lines.
Okay.
And I'll explain why in a second. Parentheses is if you have something in parentheses, you solve it first.
Right.
If you have parentheses and then something inside that in parentheses and it keeps going and it's like the further you go into the equation, there's more and more parentheses. Whatever is in the deepest layer gets done first, and you work your way out.
Start with the lowest level of parentheses first.
Right.
And the reason for that is because you're trying to treat the numbers within parentheses like numbers themselves.
Right.
Like if you have in parentheses, now everybody get your pen and paper out if you don't have it already.
Actually, we'll jump to...
There's no point.
I don't have to?
Nah. If you have in parentheses 5 plus 3, and then outside the parentheses you have plus 4, you need to treat that 5 plus 3 as if it's a number.
As if it's in its own unique world.
Exactly. So you solve that first, you end up with 8. Then you add 4 to that, and then you get 12. Because if you don't do it that way, you'd end up with, 4 plus 3, which would be 7, and then you'd add 5 to it, which is still 12, but that's just because we're adding, so don't worry about that.
That's because of what we talked about earlier.
Exactly. So anyways, you will solve parentheses first because you're trying to treat them as numbers. You'll start with the innermost parentheses when you have multiples or nested parentheses.
Here's a good example. 2 times 2 plus 2. So if you say it like that, and you followed order of operations, you'd say it's 6.
Right, because you do the multiplication first.
Right.
And then you add.
Or if you just did in order, because I said 2 times 2 plus 2. But what happens if I said 2 plus 2 times 2? Would I get 4 times 2, 8? Or would I get 6?
Right. This is where order of operations came to be in the first place.
Exactly.
That's why it's here. But then, you could divide that up with parentheses to control what you do first. Hang on. Looking for my cursor. There it is. How's it going? So let's see. If we had 2 plus 2 times 2, the order of operations dictates that we would have to multiply first. Because notice, multiplication pops in on the list higher above addition.
Right. It's an order of precedence.
Right. So we would say we would multiply 2 times 2, we get 4. We'd add another 2, so we'd end up with 6.
Right.
If we wanted 2 and 2 to be put together first, following, again, order of operations, we could put parentheses in here, so we could say, boom, now we're treating 2 plus 2 as its very own number.
Right.
So this would become 4 times 2, which of course is 8.
Right, and if you applied the distributive law, you'd have 4 plus 4, which is 8.
Exactly. So it is just a way to standardize equations so that they can be followed. So we start off with parentheses, then we go down to exponents.
And then you get down to multiplication and division. Once you hit that layer, it doesn't matter which one you do first or second. Because essentially they're the same thing. Division is multiplication if you flip the fraction. And then similarly, addition and subtraction. Doesn't matter the order you do those, because a subtraction is just addition of a negative number.
Okay.
If you think of it like that. You can think of it like adding... if you think of addition and subtraction in the way of, let's say, adding ice cubes and these heat cubes that I just invented to change the temperature of something.
Sure.
Then suddenly... It's like, if you want to subtract, you want to make it lower, you add an ice cube.
You add an ice cube.
If you want to make it hotter, make it a higher number, you add a heat cube.
A heat cube. There you go. But it doesn't matter the order in which you divide or multiply, as long as you take care of multiplication and division first.
At the same time.
At the same time, exactly. And then you handle addition and or subtraction.
Exactly.
Cool. So that is the order of operations.
And these help tremendously when working throughout all of math.
Right.
And even in all the other sciences. They help with many, many things, so always keep this in mind. Also, another time that you'll come across in the real world is if you ever want to enter one of those, let's say, McDonald's contests and win, your PSP.
Sure.
They always have a skill testing question, which, if it doesn't have brackets, expects you to follow order of operations.
I got
And
you.
if it does, they generally put the brackets in where to calculate first.
Cool. Well, I think we've reached the end of our little slide table.
I believe so.
So that is going to be the end of this first lesson in the math VTMs. Now, we've covered a lot of stuff. A lot of it was pretty basic. A
lot of it was probably review. Maybe all of it was review.
But review is good. So make sure that you have this stuff because these are going to be kind of comprehensive. We're going to assume that you know this as we move on to the next
Right,
thing.
when we move on to algebra and then we move on to systems of linear equations and calculus maybe or trigonometry. All of this is necessary. All of this is a prerequisite.
We have all kinds of exciting stuff coming around the corner in the world of math. So, Mr. DeMondo, I'd like to thank you for your efforts.
I'd like to thank you too, Zach.
And guys, it's been great. So that's going to wrap it up for this VTM, everyone. Thanks a lot.
Thanks a lot.